Hi. So in today's lecture, I'd like to talk to you about a review of free body diagrams and also an introduction to friction. So you may remember that free body diagrams are pictorial representations of all the forces that are acting on a particular object, and they're very useful for being able to solve problems using Newton's laws. So what you're going to do in free body diagrams is you're going to model the object as a particle. Now, I'd like to emphasize that you don't have to be a good artist here. I am a terrible artist. You can represent any object that you like to as a box or a dot or a circle. It doesn't matter, just so long as you get the forces right when you draw them on the paper. The forces should be drawn as arrows, and the arrows are acting in the direction of the force, so you want to point the arrow, make sure you draw an arrowhead and not just a line, and then point that arrow in the direction that the force acts. You'll also want to label any angles that you might have for the force vectors, okay? So for an example, here is a free body diagram of a stoplight. And what's happening here is that the stoplight is hanging from a cord which is tied to two other cords. So the relevant forces here are, of course, the tension. And so for example, if you look at the knot on the cord right there, then you have a tension pulling downward, right? That we call tension 3 because there's really 3 tensions here. And then you have tensions 1 and 2 acting at an angle as shown in this diagram. Okay? So here we've got all the key parts of a free body diagram. Our knot here is just a little dot, so that's okay. And then we have our force vectors as arrows, and we have the angles labeled. Okay. Now, once you've got your free body diagram drawn, what you probably really ultimately want to do is to solve a problem involving the motion of that object. So although each problem is different and has its own little quirks and problems associated with it, the way to solve each one of these problems is really the same. So first you'll draw yourself a little sketch of any objects that might be associated with the problem. So for example, here there's a little boat. Okay, so there's a little boat. So you draw your little sketch. You might draw the boat as a boat if you're good, or if not, then maybe you would just draw it as a box. Now, once you've got your sketch done, then you add the free body diagram, the force vectors, to your sketch. Okay, you want to make sure that you draw all the forces that are acting on the object. You want to make the magnitudes proportional, so if you know that one force is much larger than the other, then you want to draw that with a longer arrow than you draw the little forces. It helps you conceptually understand what's going on. You also want to make sure that you label the angles as accurately as you can. You want to give each force vector in your drawing a name, right? Labeled with an appropriate vector symbol with an arrow on top, okay? Given a name. And then, once you've drawn your free body diagram, you'll go on further. You'll take those vectors that you've drawn in your diagram and you're going to resolve them into their component parts. And then, for each direction that you have, x, y, maybe even z, you're going to apply Newton's second law to each component. So you'll set the sum of the forces in that direction, say the x direction, you'll set the sum of the forces equal to the mass of the object times the acceleration in that direction, say a sub x. Okay? So you'll apply Newton's second law to each component. Then once you've got that done, you have a system of equations that you can use to then solve the problem for the acceleration, or if the acceleration is given, maybe it's asking you for the magnitude of one of the forces, or the mass. And like I said, each problem will have its own little quirks to it, so it's just depending on what you need to solve for in that problem. Okay? So for example, I want to do a real quick example here. This one I call weighing a fish in an elevator. All right, so here there is someone that is inexplicably trying to weigh a fish while they're riding in an elevator, which is something I don't recommend, as it's probably a rather smelly endeavor. But here we go, nevertheless. So let's say that you've got a person and they're weighing a fish. Now we know the mass of the fish. This fish has a mass of 4.08 kilograms. Okay? And we want to evaluate what the scale says that this fish weighs if the elevator is moving with an acceleration of 2 meters per second squared upwards versus the elevator is moving with an acceleration of 2 meters per second squared downwards. So, if you hadn't guessed already, what happens is that the apparent weight of the fish is going to be different in each of those situations because of the motion of the elevator. even though the pull of gravity on the fish is really the same in both conditions. That force is the same, but the motion of the elevator messes with the reading, okay? So let me show you what's going on here. Steps 1 and 2, the sketch and the free body diagrams, are already solved on this. Now this is a one-dimensional problem. Our motion is all in y, so that makes things a little bit easier. So for example, for this fish here on the left, when the net acceleration is going up, we have a tension in the line that's holding our fish onto that scale, and that's going up. And then the other force that's acting on the fish is gravity going down. Okay, those are the only two forces acting on the fish. Now, if the net acceleration of the elevator is different, then maybe that affects the reading of the elevator, the reading of the scale. And the reading of the scale would be because of the tension that the fish pulls on the line. So that might change the length of that vector, but the vector itself is still pointing upwards, and it's still there. And then we still have mg going downwards. And since the fish's mass is the same in both cases, the force of gravity for the fish would be the same for both. Okay? So those are our free body diagrams. We've got it all labeled, everything nicely done there. So now let's move on to steps 3, 4, and 5. Okay? We're going to write our vectors into their component parts. So we've got the two vectors, okay? Two vectors, tension and gravity, okay? So we have a one-dimensional problem. We're going to call up positive, we're going to call down negative, okay? So if I were to write the y component of my tension, which I call here t sub y, I'm just going to call that plus t. The plus sign is because the tension points up, okay? And t is for tension. I don't know what tension is, so I'm just going to leave it as t. Now, mg, the y component of gravity here, mgy, would be equal to the mass of the fish times the acceleration due to gravity. Now the acceleration due to gravity is minus 9.8 meters per second squared. The minus sign means down. Okay? So plugging in for that, we have mgy is equal to 4.08 kilograms, that's the mass as was given in the problem, times minus 9.8 meters per second squared. And like I said, the minus sign is down. Now this would be the same for either question, whether the elevator was moving up or whether the elevator was moving down. These would still be our vectors and our symbols for them in the equation. But now we're going to apply Newton's second law. We're going to sum up the forces in the y direction here, since that's the only direction of interest. We're going to sum up those forces, and then we're going to set them equal to the mass times the acceleration of our object. Okay, so here we go. Let's do the going up elevator situation first. If the fish is in the elevator, right, which it is, then the fish will be accelerating in the elevator. It will be accelerating along with the elevator. So that means that our sum of the forces in y is equal to the mass times the acceleration. It'll be the mass of the fish, which is 4.08 kilograms, times the acceleration of the elevator. Okay, now this is for the y direction. Okay, we're just taking the sum of the forces and equations in one direction at a time. We're applying it here. So if the elevator is accelerating upwards at 2 meters per second squared, then that's going to be plus 2 meters per second squared. Okay? Now that's going to equal to the sum of our forces. We already wrote our forces up here in the other step. So plugging in for those, it's going to be the sum of the forces, t minus 4.08 kilograms times 9.8 meters per second squared. All right? So now we can solve. That's our last step. We've plugged into our sum of the forces equations, okay? And now we can solve. So solving for t, what we would do is we would add the 4.08 times 9.8 to both sides of our equation, and we would end up with t is equal to 4.08 kilograms times 2 meters per second squared plus 4.08 kilograms times 9.8 meters per second squared. The minus sign goes to a plus when I take it to the other side of the equation. Now, following through on my little calculation there, I end up with a tension of 48.1 newtons. So our scale would read 48.1 newtons for the fish weight when it was going up, okay? Note that this is more than the true weight of the fish, which would just be mg. All right, now let's say that it's going down, okay? Our vectors up here, our tension and our gravity, are going to be the same written out in terms of their symbolic notation. So I can use the symbolic notation that I used for the fish going up into this second equation. What's changed though is that now the elevator is going down. So when I apply the sum of my forces equation, it's going to still be equal to ma, which is still the mass times the acceleration in the y direction here since we're in a one-dimensional problem. But now our acceleration is downwards. And so we symbolize that here with a minus sign, okay? So the downward acceleration would be 4.08 kilograms, the downward force would be 4.08 kilograms times minus 2 meters per second squared. The minus sign comes because it's accelerating downwards in the elevator and the fish is in the elevator. Okay? And now that's going to equal to the same sum of the forces as before, T minus 4.08 times 9.8 meters per second squared. So now when I solve this equation for T, I get T is equal to minus 4.08 kilograms times 2 meters per second squared plus 4.08 kilograms times 9.8 meters per second squared, and that gives 31.8 newtons. So the fish feels lighter when the elevator is going down. Okay, now I want to talk about forces of friction. So, as you probably remember, a force of friction is when you have a resistance to a motion or a push, okay? So this resistance to the direction of motion or to the direction of intended motion is due to the interactions between the object and its environment, okay? And that resistance is called the force of friction. Friction always acts tangentially to the surface, okay? So for example, if I'm trying to rub my hands together, I'm going to get a resistive force. And for example, if I'm shoving this hand upwards, the force of friction would act downwards, okay? But it's tangent to my hand, which is the other surface, right? Along the direction of the surface. So friction acts tangentially to the surface, and it always opposes the direction of motion. So that's how you know what direction to draw your arrows in that free body diagram. Now you can have friction whether or not an object is moving. Like let's say that I'm trying to push something that's really, really heavy, but I haven't yet pushed it hard enough to get it going. I've still got a force of friction in between the object and the floor, right? I've still got a force of friction there that's keeping the object from moving forward, okay? Now, if the object isn't moving yet, that's called static friction, and it means that the object is not sliding with respect to the surface. Now, if the object is sliding with respect to the surface, like my hands here, then that's kinetic friction, okay? So kinetic friction, sliding with respect to the surface, static friction, object's not moving yet. Now the magnitude of the kinetic friction is usually less than the magnitude of the static friction, even if you're considering the same object on the same surface. So let's say that I'm trying to move a couch, and I'm pushing the couch, and I haven't yet quite pushed it hard enough. All of a sudden, I exceed the force of static friction with my push, and then the object begins to slide across the floor, okay? Once it slides across the floor, it's easier to keep the object moving than it was to get it moving in the first place. You've probably noticed that if you've ever tried to move a big couch, okay? Now sometimes drag will also be referred to interchangeably as a force of friction, but to be clear, drag is considered slightly differently. That's when you have an object in motion through a viscous medium like air or water or maple syrup, okay? And that's due to the drag of the medium on that object through it, okay? So, yeah, some texts will refer to it as a type of friction, and some texts will differentiate and call it drag and be specific about that. All right, now let's get back to the sliding friction, okay, and the kinetic friction. So in those cases, when you have an object sitting on a surface and you're trying to move that object across the surface, trying to get it sliding, okay, your friction is proportional to the normal force. Remember that the normal force is a contact force that acts perpendicular to the surface. So for example, if I push down on this table, the table pushes back. The table pushing back is the normal force that the table is exerting on my hand, okay? So this frictional force is going to be proportional to our normal force. The constant of proportionality is called the coefficient of friction. So you could write that the force of static friction will be less than or equal to the coefficient of static friction times the normal force. And you could write that the kinetic friction will be equal to the coefficient of kinetic friction times the normal force. Okay? So these equations here, those are the magnitudes of the forces on the slides. Just the magnitudes, all right? So why the less than or equal to sign in the static friction? Well, that means that the equals sign is only going to be valid right at the threshold, right when you're getting ready to be able to push that object past it. Before that, your object will always be able to exert just a little bit more force to stay still. So that's why the less than or equal to sign there. Okay? It's also important to realize that unless you're looking at the nanoscale or the microscale, these coefficients of friction are nearly independent of the area of contact. Okay, so static friction acts to keep the object from moving. If your force increases, so does the static friction, up till it reaches that threshold at which motion will go. Okay, motion will occur. So that's why the less than or equal to sign, the force of static friction will be less than or equal to the coefficient of a static friction times that normal force. And the equality only holds when the surfaces are right there on the verge of slipping. So if I were to draw this in a free body diagram, here little n is my normal force going upward, mg is gravity acting downward, and then I'm giving it some kind of push, F, to the right, say, on this trash can. And then the static frictional force points to the left because I'm trying to move the object to the right, and it's going to oppose the direction of the push. Now once I get it going, right, now my kinetic friction, now my friction arrow is going to be smaller in length than my push, right, arrow. Still normal force and gravity acting down, force to the right, kinetic friction to the left. Okay? We're going to neglect for now any variation that the kinetic coefficient of friction would have with speed. Although it has been shown to have a small dependence, we're going to ignore that for now. Okay, so for example, if I had this trash can and I were starting to push it, say it was really full with lots of trash, and I were trying to push it and get it going, I would have to push until I finally exerted enough force to get it to slide across. You can see that the force of my push and the static friction equal each other right up to that threshold when I started moving. Then I see a drop in the amount of force, right, that friction exerts, and then I have this constant force of kinetic friction exerted after that. Okay, so that's what happens. You might be wondering what magnitude these coefficients of friction are. Usually your coefficients of friction are numbers less than 1. And since you've got a force on the left-hand side and a force on the right-hand side, this coefficient of friction is just a constant of proportionality, so it's dimensionless. Okay? So for example, metal-on-metal contacts have rather high coefficients of friction, whereas ice-on-ice have low coefficients of friction down here. Okay? So you can see the difference there between the various coefficients of friction. So since friction is just a force, just like any other force, you draw it on your free body diagrams and you include it in your sum of the forces equations when you do your Newton's law problems. Okay? Let's do an example problem with that. Let's say that you've got two children and they're sitting on a sled on the snow and they're being pulled. The sled's being pulled by a rope that makes an angle of 40 degrees with the horizontal. The children have a combined mass of 45 kilograms and the sled has a mass of 5 kilograms. The coefficient of static friction is 0.2 and the coefficient of kinetic friction for the sled on snow is 0.15. So what's that threshold force needed to overcome static friction? Okay? So, step number 1, you draw yourself a sketch. Here's my sketch, okay, so you can see what kind of artist I am. I have two little stick-figured faceless children sitting on a sled, which is this little curvy thing right there, and then the ground is symbolized by my x-axis here, okay. Now, my free body diagram for this, I'm going to draw all the forces that are acting on the children. So I've got my normal force acting up, right, and that's from the sled on the snow, right, normal force acting up. And then I've got gravity downwards, mg. I've got my frictional force. Here, static friction is what I'm concerned with. So I've got that acting opposite or tangential to the surface, but opposite the direction of the pull. So that means that F sub s points left here, okay? And then I would have some rope, right? And the rope I'll call a tension T, okay? And that's going to be at an angle of 40 degrees with respect to the horizontal as it's said in the problem. So there's all my forces. All right. Now, if there's static friction, then there's no net motion. So I indicated that on my drawing just to make sure that I emphasize that point. Okay, the next part says to take the forces and break them into their component parts, right? That's the next step. So that's what I've done here. We've got both x and y components in this problem. Okay, so it's a little more complicated than my fish in the elevator problem. So I wanted to write out the components of all my forces in the x and the y. So here I go. My normal force, it's got no x component. It's just in the y. So the normal force component in the y, I'll just call F sub n. I don't know what the normal force is yet, so I'm going to leave it in symbolic notation. mg, that also doesn't have any x components, right? As I've drawn it here, x is parallel to the ground and up and down is y. So mgx is equal to 0. But mgy would be the mass, the combined mass of the kids and the sled, and then the acceleration due to gravity acting downward minus 9.8 meters per second squared. So mgy would be minus 50 kilograms times 9.8 meters per second squared. When I multiply that through, I get mg is minus 490 newtons in the y direction. The tension, okay, this is the only force that I have that has components in x and in y, okay? Using my trigonometry, I can see that there's a 40-degree angle here with respect to the x-axis. So the x component of my tension vector is t times cosine of 40. Now I don't know what the tension is. It didn't tell me in the problem. This is one of the things I'm going to have to solve for. So t is not known, so I just leave it symbolic. The y component of the tension, if I use cosine for the x, I have to use sine for the y, so the y component of the tension would be t sine of 40. Okay, the static friction, okay, writing that out into its x and y components, there are no y components of static friction. It's acting tangentially to the surface, and the surface is x. So Fsy is 0. But Fsx, right, it acts in the negative x direction, so I'm going to write that as minus mu sub s F sub n, okay? Remember that the force of friction is the coefficient of friction times the normal force, so that's where that comes from, okay? Now, I know that I'm concerned with static friction here. So the coefficient of friction they gave me for static friction was 0.2. So I go ahead and plug that in. So my force of static friction in the x direction is minus 0.2 times F sub n. But I haven't solved for F sub n yet, so I leave it in symbolic notation. Okay, so I've broken my vectors into their component parts. The next step is to plug it into the sum of the forces equation. So here, I've got two sets of equations, right? I've got a sum of the forces in x and a sum of the forces in y. Now, in this question, it asks about static friction. What's the threshold force needed to overcome static friction? That means nothing's moving, okay? So the sum of the forces is going to be equal to 0 because there is no net acceleration. So the sum of the forces in x is equal to 0. Now I sum up all the forces that had an x component into them. So that was tension and friction, okay? So the x component of my tension was t cosine 40, and the x component of friction was minus 0.2 F sub n. So for the sum of the forces equations in x, I have 0 is equal to t cosine 40 minus 0.2 F sub n. So now I look at the sum of the forces in y. The sum of the forces in y is equal to 0. That's equal to all the forces with a y component. I've got tension, normal force, and gravity. Okay, so summing all those up, t sine 40, that's the y component of the tension, plus the normal force, an unknown, right, plus F sub n, and then gravity, minus 490 newtons. Okay? Now, you'll see here, I'm not done yet, right? This isn't a one and done kind of thing. Here I have two equations, but I also have two unknowns. Remember that you have to have the same number of equations as unknowns in order to solve a problem. Great. So now here we are with our algebra, okay? We really want the tension, okay? That's what we really want out of all this. Okay, so we're going to use our x equation. We know that we really want a tension because it says what's the threshold force needed to overcome static friction. So that threshold force would be how hard do you have to pull. So since we really want the tension, we're going to use the x equation. We're going to solve for that first. So here we have t cosine 40 minus 0.2 F sub n is equal to 0. Solving by adding 0.2 F sub n to both sides, I end up with t cosine 40 equals 0.2 F sub n. And if I solve for F sub n, that's equal to t cosine 40 over 0.2. Doing it this way enables me to plug my normal force into my other equation and eliminate it, leaving only one variable, the tension, which is what I really care about. So now taking that equation that I had for the sum of the forces in y and plugging in for the normal force, I can solve for tension. So now I have t sine 40 plus t cosine 40 over 0.2 minus 490 newtons is equal to 0. Okay? So I take that 490 newtons and I add it to the other side. And then I take the stuff that multiplies t that remains on the left-hand side of the equation and I factor out t. When I do that, I end up with t times sine 40 plus cosine 40 over 0.2 equals 490. Okay? Solving for all that stuff, what I end up with is, if I multiply, or if I solve computationally, sine 40 plus cosine 40 over 0.2, right? Then that I end up with t times 4.47, okay? So dividing both sides by 4.47, I end up with t is equal to 109.5 newtons. So that's the threshold force that I have to apply to get the thing moving in the first place. Once I exceed 109.5 newtons, the kids will start to slide on the snow. All right? Okay, well, I hope that was a good review of free body diagrams, a little bit about how to solve free body diagram problems, and a nice introduction to the forces of friction. I'll see you in class.